So we're going to head back to just straight geometry. Forget about algebra, and we're going to go back to that time before the two subjects were kind of connected. So in geometry, there's a group of two-dimensional shapes that can be made by slicing a set of cones in various ways. So these two cones, imagine like two ice cream cones stacked on top of each other so that the points are touching. So the bottom one's upside down and the top one would be right side up. Now, if I take a piece of paper or a plane and I cut these cones in different ways, I'm going to create these different shapes, which are called conic sections. So the first one here, if I take, it says the circle is made by slicing one cone parallel to its base. So if I go straight across through a cone, I will get a perfect circle. It could be that bottom cone, it could be the top cone, but it'll make a circle. If I take that piece of paper, which we, as I said, we call a plane in geometry, and I tilt it just a little bit, we get an ellipse. So if you think about this, this is like, the path of the planets around the sun. That's where we hear that word ellipse if you're in earth science. So it says the ellipse is made by slicing one cone at an angle not parallel to its base, but still cutting all the way through one cone. So I could tip it at different angles, which would change what we call the eccentricity of that ellipse, but basically has to be in that direction. Now, the next thing I could do, if I kept tipping it right further down to this picture, we could tip it to a point where the bottom of the plane kind of came out of the bottom of the cone, but it's still not tipped so much that that top cone is cut. So basically, the parabola is made by slicing one cone at an angle not parallel to the base, so not a circle, without cutting all the way through the cone. So this one was still cutting all the way through the cone. This one is without cutting all the way through the cone. And here, that intersection creates a parabola. Now we're going to kind of pretend those cones are infinite to get like an actual parabola, but that's the idea. The last one is called a hyperbola, and this is if you take that plane and you tip it so much that it cuts through both cones. We got this thing that kind of looks like a double parabola. It doesn't have the same exact shape. Okay, but this with the two pieces is called a hyperbola, okay? These shapes were known about and studied in geometry before the invention of the coordinate plane. So down here at the bottom of the page, we see these shapes, we see the different cuts. So we have our ellipse, right? And you can see the diagonal cut, the circle is straight across. A hyperbola, this one's actually straight up and down the way they cut it, and then the parabola on the side. And then there's the pictures of what the cross sections or the cuts look like, and that's where these names come from. So we have ellipse, circle, hyperbola, and parabola. So on the next page, we're going to look at and we're going to graph another expression, just like we graphed 3x plus 1 on the other page. Here we're going to graph negative x squared plus 4x plus 5. So in the interest of time for this video, I graphed this parabola. Hopefully the points are okay to see just kind of quickly. This is right 0, 5. This one up here at the top is 2, 9. So I would pause it and just draw that. So once you get it drawn, I just want to reiterate what I can do to find these is just take this expression and pick different numbers for x, right? Which is basically where we get a table from when we're graphing. Okay, so hold on a second, I think sorry about that. Something went wrong with my pen, so I couldn't underline. So basically I'm just taking different points, so I didn't do it randomly, but I plugged in a 0 and I saw that this gave me a 5, right? And I plugged in a 1 and I saw that it gave me an 8. Now what happens is, when I look at this shape is the same shape as with those two cones. When I cut them with the plane at that angle, like this, and it formed the parabola. So that's like about as ugly as it gets, but it's really hard for me to draw it with these pens. Now it's not just, oh, it looks like that shape. Every single way it changes and fits in, it's the same exact shape as what had been studied forever on these cones, just happened to be made by this type of expression. So the shape is a parabola. And this algebraic expression, once we graphed it, we could start to answer those same questions. So we're going to answer kind of similar questions to what we did with the line on the other page. So it says, using the x-axis as a reference, what is the height of this equation when x is 3? So I can talk about how tall this is, right, which is a geometric question, and that's 8. When it crosses the y-axis, right, the height is 5. And if the slope of the curve is always changing, what is the slope at x equals 3? So I'm right here, and that's a really tricky question because we're saying, well, what's the slope right there? But everything we know about slope, we have to take 2 points and do y2 minus y1 over x2 minus x1. So there's like different things we could try. Maybe we could pick points on both sides and find the slope between them and say, well, that's kind of close. But right now, this is kind of something that we can't answer with the math we know. Okay, so with the line we could, and when that coordinate plane was invented, it was also a question they couldn't answer. They saw these graphs and they were like, well, it might be interesting to know what the slope is in different places, but they didn't have the tools yet, or they hadn't figured out how to find those slopes. So the next question that comes in, if we were to create a shape between the y-axis, so let's outline this, the y-axis, the x-axis, we already have this line drawn in for the height, so the line x equals 3, and this curve. So I'm just going to erase that bottom little bit that I drew just to kind of show that that's the shape we're finding. So here's another question, seems kind of interesting. What do I think the area of this is? But we know the areas of like rectangles and triangles and these nice shapes with straight lines on the sides. We even, and actually really as a result of calculus, which we're going to talk about in a second, can find the areas of circles. But what about this curved piece here? Like, how would we handle that? So while the coordinate plane let us see the geometry of algebra, it also brought up some new questions about how do we do these things. But even though they were new questions, they were actually old questions people wondered about for a while, because we can have curved figures that aren't on the coordinate plane. So going down to the bottom, this is, part of the lesson we're connecting geometry and algebra, and part of it we're starting to talk about questions people have asked. So it says the last 2 geometric questions, the slopes of curved lines and the area of curved geometric figures like the conic sections, frustrated mathematicians doing traditional geometry for thousands of years. So as I said, they thought about this stuff like, what do I do with these like curved figures, and how do I harness them and figure things out about them? And they had ideas about, slicing things into tiny pieces and adding them up together, but they needed the power of variables and the patterns of algebra to get control of these geometric problems. Okay, so the problems were there. The coordinate plane was kind of conceptualized, and they started to put these algebraic things on there. They also said, oh, here's some geometric figures that end up on the coordinate plane from algebra. And as soon as the coordinate plane came about and these 2 areas of math were brought together, the answers actually came pretty quickly. So it says the concepts and methods developed shortly after Descartes invented the coordinate plane. Taken together, the question above, as well as other ones that can be asked about the shapes or graphs of algebraic functions, revolutionize the way we live in every aspect of life, because patterns and change are everywhere. So when we ask about the slope of a curved line, if that line represents the distance a car has traveled, we're talking about the car's velocity, right? Or if we know the velocity, we're talking about acceleration. So all of these things that happen in life, maybe it's the pattern of a disease, like how is the disease increasing? If we could get a graph, like I don't know if you guys have seen like those COVID graphs online, if we could take that graph and think about it algebraically, right? The graph is a geometric figure. Could we figure out these patterns of change? Basically, and I have a list here, speed, financial matters, organism growth, disease management, mechanical processes, ocean tides, hormone fluctuations, crowd control. basically, once we had the coordinate plane and we could use algebra and geometry together, they quickly figured out how to solve these problems and created the math that is calculus from it. So human progress since the mid-1600s has involved quantifying and then harnessing these patterns. And we're not going to get too much more into it here, but just an awareness that when you graph things, that wasn't always there. And that ability to graph functions and talk about them geometrically has a huge impact on all of our lives. Probably our life expectancy would be way lower. We probably wouldn't have any free time because a lot of our industrial revolution advances, our phones, everything is kind of based on quantifying these patterns and figuring out how they work.